This is one of the most used and utilized product in any photonic or electronics industry in India as well. So you can get benefit out of it in case you grasp and learn how to make use of various kinds and types of applications, optical based applications using this tool. So it is very important uh, for you to participate in this short discussion. And in case you have any query, definitely I will resolve it there and then. So shall we start now?
Yes, sir.
Okay, great. So once you install this, I think you are aware that you can start this through this toggle, that is Windows based selection from this section. You just need to click here and open this tool from this section. So once this system is installed, during the installation of this whole simulation software, you must have installed the sample files. So these are the install Optisystem samples. You can open this open sample toggle, or this toggle is directly available in your documents under Optisystem 22.1 samples. So these are the list of applications, various kind of applications which are published in the form of you can say the uh, the kind of a patented research in the form of research papers, as well as the papers and the layout diagrams from the vendors itself. Vendors means those who have fabricated it or have utilized these kind of concepts into their manufacturing facilities. So basically, if you want to start with introduction, just look into this introductory tutorials, double click on this, and you can get to know transmitters, subsystems one by one. You can go around with the various kind of lessons using this introductory tutorials. Also, for example, if you want to do some analysis of your own, just open, for example, pre-post and symmetrical dispersion compensation fiber. So this is basically a concept where an optical fiber has been used for making a communication link, and we are using dispersion compensation fiber to compensate the dispersion across a whole link. So here are three methodologies: post, pre, and symmetrical. So in these three methodologies, what you can do is like, first one is post, means if this dispersion compensation fiber is connected after the single mode fiber. This SMF is nothing, just a generic optical fiber, and I have given the name SMF. Its length is 120 kilometers, and we have rest of the fundamental properties of optical fiber. So after this transmission, this loop control will control the number of cycles of this communication channel. It means this is very similar to a kind of programming. You must have heard or learned about object-oriented programming, and you have gone through for loop or while loop or any kind of looping arrangement or programming. So in the same scenario, this loop control is utilized here. So this loop control has given two numbers, means it will run for two times. So once your data has been injected through this section after modulation, this loop control now passes the data through single mode fiber of 120 kilometers. Then EDFA amplifier is used here to pump or to amplify the signal. Then the same has been passed through a dispersion compensation fiber of 24 kilometers of length. Then again amplifying the data, coming back to loop, and then again the second loop. So this will run for 2 times, and once the loop is finished, it will go to the receiver section, and there you can do the analysis like BER for quality factor and other arrangements. So basically this is for post, means dispersion compensation post of single mode fiber, and pre means dispersion compensation before this single mode fiber, pre of single mode fiber. So in the same way, you can see the comparison, and symmetrical means the combination of post and pre, means dispersion compensation fiber pre of single mode fiber, then connected to again the post arrangement, means after this single mode fiber. So this is a combination of both, and here the loop control is for time. For pre, the loop control is for 2 times. So accordingly you can make a arrangement where you can compare these 3 layouts and analyze which arrangement of dispersion compensation fiber is better. So if we simulate this concept, so now if I go to post, where dispersion compensation fiber is connected after single mode fiber, so its BER or quality factor, you can say quality factor is 66.1. Then for pre, it's 58.0, and then symmetrical means combination of both, it's 62.5. It means the post arrangement of this optical communication link for dispersion compensation fiber is better for the post factor 66.1. After this post, symmetrical is better, it's 62.5, and then at last the pre-arrangement. So this is how you can compare this. So this is one of the example you can go through. If in case this samples are not installed, you click here, go to the Optisystem folder and click here on install Optisystem samples. You can install it externally as well if it is not installed along with this whole tool. So this whole layout section will be installed in your system. Okay, now for example, optical wireless communication, and let us use this FSO universal channel. That will be a bit complex for you. Just a second. Optical wireless and indoor optical link. Okay, for example, if it is a Li-Fi model, Li-Fi multipath modeling, if we say, I do hope everybody knows about Li-Fi technique. Let me tell you if you don't know about this application. Li-Fi means light fidelity. It means instead of utilizing Wi-Fi for getting the services of internet or any broadband service you are utilizing in your homes, in your institute, or like wherever you go, you can have an easy access to Wi-Fi. That is fine. You have a router connected with optical fiber which reaches your premises, and from that Wi-Fi the signal is transmitted and your devices catch the particular signal and you are taking that services on your particular device. That is fine. But in case of Li-Fi, light fidelity. It means you are utilizing LED LED light for the transmission of signal, utilizing in your applications instead of Wi-Fi. So Wi-Fi is the same concept. For example, in your classrooms, in your conference rooms, you must have LEDs fixed. And what if that LEDs provide you this facility? Means you are getting 4G or 5G signal or something like that. So I request you to read this Li-Fi technology or application through Google. You can search it. You can go through the Li-Fi papers. So in the same case, transmitting some random sequence data means some random data we have generated, and that just a second, and that random data is basically passed through LED. Means now LED will be utilized for your transmission or receiving purpose. So it's too late, those who are joining right now. Anyway, uh, so here LED is getting electrical signal, electrical pulses from NRZ pulse generator. And NRZ pulse generator is basically pulsing or creating the pulses utilizing the binary data, that is your own data, in the form of like text, images, video, or anything. So this data is converted into electrical pulses in NRZ format. Then it is fed to LED. Now LED works on VLC, visual light communication or visible light communication. So as per the visible range, 350 to approx 750 nm. So we have mentioned here 450 nm, and these are the other specifications of a LED. So accordingly, in case you have LED and you know about the technical specification, or you have the data sheet of that product with you, you can find these kind of specifications, or you can reach out to a vendor to provide you the slope efficiency, quantum efficiency, RC constant. So they have all the data with them. So accordingly, you can feed it here, or you can go through this by default value of LED. So LED is basically available inside this default under transmitters, optical sources, and this is LED. So you can feed this and you can utilize this. Okay, so once the electrical pulses are fed to LED, this is injected or transmitted through a LED. And as per the physical scenario, just imagine that LED distribute its light in the corresponding way. Like if it is on the top, so it will provide the direction 45° left and 45° right, and towards perpendicular. So in the similar way, we have distributed the LED frequency with the power splitter, and again with the power splitter. So basically, this part is depicting as the power distribution or intensity distribution of an LED. So because we are like with the single power splitter, again a power splitter is connected, then LOS, and then again a power splitter. So here we have provided optical attenuator in case you want to attenuate or fluctuate the optical signal. You can do that. You can attenuate it. And here the distance is given in 100 meters. So 100 meters, it is like huge. So basically it is merely 15 meters or more than like not more than 10 meters. So your roof is not more than 10 meters or approximately 10 to 15. If it is a conference hall, then it may be like 15 to 20 meters of a height. So you can mention the distance. Instead of 100, you can feed 20 meters. So this distance or range of LED can be positioned as per your own R&D scenario. So it's all about the imagination, or you can see the practical application aspects. You can feed that, and then at last this power is combined and it is amplified through an optical amplifier. Then the optical fit component will fit this signal, and then it is received at a receiver. And for making it as a it should look like a practical scenario, we are adding a external ambient noise source, because in your surrounding area there is a natural behavior that you should have some noise externally. So we are using it for with the electrical adder, and at last with the trans impedance amplifier, we are detecting it through a DC block, and at last we are calculating it with the BER analyzer. So accordingly, you can simulate this kind of setups in your own application scenario. You can choose it through sample files. Also, in case you are interested for any kind of WDM applications, so we can very well discuss about it. For example, in case we have here WDM design. So WDM design means on a single optical fiber. Means, for example, if you talk about an optical fiber, it is never a single channel optical fiber. It must have 1, 6, 12, 24, 96, and even 126. So these are the like multiple bunch of optical fibers packed inside a single cable. Because in case you want to work utilizing multiple applications, so WDM is the best application scenario. WDM means waveguide division multiplexing, or wave division multiplexing. So here waves, or you can say the wavelength, is basically divided utilizing mux, and then at a receiver section it is demultiplexed to extract the various applications which are traveling through a single optical fiber. So here, this is an example. First of all, uh, okay, so you can go through one by one. So here I will explain you, because this transmitter channel and this is a receiver. So you know this fundamental, right? So here this WDM mux. So if you want to search for this component or for any component, right click, find component, all words, and then type WDM. So this will take you to multiple WDM components, and from here you can, for example, this is WDM 2 by 1, 4 by 1, and so on. So if you double click, you will reach at the multiplexers library. So under default, we have a WDM multiplexer library and then multiplexers. So because this is having 1, 2, 3, 4, 5, 6, 7, 8 channels. So this is 8 by 1. So 8 various frequencies. Various frequencies means first laser is working on 193.1 terahertz. Second laser carrier is 193.2. Then 193.3. And last one, 193.8. Means you have these 8 frequencies, and every frequency is utilized for its individual application. For example, your telephone line, your internet broadband connection, your security surveillance system, your ATM machines, and so on. So whatever the application you have, that the bunch of applications are traveling through a single optical fiber, but we are utilizing this WDM concept or WDM application where you are using all various frequencies, muxing it or bunching it using WDM muxer. And under WDM muxer, you need to specify the channels and their frequencies, and you can pass it through a optical fiber. Say here we are utilizing 80 kilometers and number of loops are 3. 3 multiplied by 8, it's 240 kilometers, amplifying at each loop. And again, after that, 10 kilometers, 100 kilometers of optical fiber. And once we are sure that, okay, it is fine, we have sufficient length, then you can separate this with WDM demux. So we are demultiplexing it, detaching, or like you can say bifurcating the various wavelength. So that is the only reason the name of this application is wavelength division multiplexing. So you are utilizing this for dividing the various wavelengths into various application segments and distributing each application wherever it is required. So after this optical fiber, one user or one wavelength or frequency is distributed to a campus. Second one is to some industry partner. Third one is to bank. Fourth one is to some telecommunication exchange, and so on. So now you can connect your this BER analyzer across this section. For example, instead of connecting BER analyzer, just a second. So we are back. So again, go to this section, introductory tutorials, and this is WDM system design. And at receiver section, if I add this 3R generator across this section, and then under electrical, I'm adding this PER analyzer just to analyze what is distributed in this frequency. You can connect this whole scenario at each port. So right now, if I calculate this one, just a second, single sweep. So calculation is finished. So this is like maximum Q factor is 0. But what you can do is you can increase the power section. For example, at this WDM mux, you are getting an optical spectrum for each wavelength. 193.1, 2, 3, 4, and up to 8 wavelengths for each application. And you can see the other factors like OSNR, SNR, signal to noise ratio, and optical signal to noise ratio. And at last, like for example, if I just